Victoria Volodina. I'm still finishing my PhD with Danny Williamson, but I started my postdoc at Alan Turing Institute with Chris, Peter, Jim, and Henry. So, as I understand, last week you had some talks about uncertainty quantification, Gaussian process simulators, and collaboration, how they're amazing for temporal spatial stuff. But today I'll just go back to basics, how to construct a simple Gaussian process simulator for single output model and perform history matching. And then lots of this work has been done with Danny and James, who is a postdoc at Exeter, and we have actually code provided. So in the end, if you are interested to do some coding or would like to have access to our code that does emulation history matching, you're more than welcome to play and ask any questions. But anyway, so my PhD was mainly in uncertainty quantification, which focuses, uncertainty quantification field is focuses around quantifying and taking into account different sources of uncertainty, such as parameter uncertainty, model discrepancy, and model error. And in uncertainty quantification field, we primarily work with computer models. So we are trying to link the computer model outputs and to learn something about some physical processes that's going on in the world. So in my case, during my PhD, I worked primarily with French climate modelers, and they were really interested in, for example, in improving the cloud parameterization scheme to give a better representation of the cloud that we observe in the real world. So the idea is that we consider a complex computer model as a mathematical function f that takes some input parameters x's, which in this case are some vector length p, and returns some outputs. It could be a scalar, a vector, a matrix. So a vector could be a time series, a matrix could be some spatial temporal output of a climate model, let's say. And we model this, we develop a statistical model for this scalar output, f of x, which is given here. And it's effectively sum of three processes. So the first process tries to explain the global response behavior across the input space. And it looks like a regression function with some unknown parameter beta. The second term, epsilon of x, tries to explain the local deviation from the global response. And what we usually model this residual term as a Gaussian process with zero mean and some covariance function pre-specified by us. And the last term, eta of x, it's a nugget term, and we model it as a normal with zero mean and some uncorrelated variance, which responds tries to explain some uncorrelated residual. So it's like a noise process, let's say, in your computer model. Then we, working in the Bayesian framework, we specify prior for f of x, which is f of x given all your unknown parameters that you've seen in the previous slide. It's just Gaussian process with this mean function and the covariance function. And then we assume that we obtain some computer model runs f at some design points x, and we're able to use them to learn about to train our emulator. So we update our f of x as a Gaussian process with mean or expectation given your observed data and your parameters and covariance function as well. So you can see that you use information, your design points, as well as simulation run inside of your mean and covariance. I think it's the last slide with maths for now. So this is
Victoria, could you explain what the H's are?
yes. Thank you.
That's
So
all right.
H is your regression functions. So there could be linear terms of x, they could be quadratic, they could be Fourier series x. And they're usually pre-specified by us in the process, so they are known. They're not, whereas these parameters are unknown. Another thing is your correlation function or covariance function. It's also, the form is usually pre-specified. So this is just to demonstrate what the Gaussian process simulator looks like on a really simple 1D function. So the idea is that we're trying to model the behavior of this red, I think it's sine curve. And we observed the sine curve behavior exactly at the 5 design points, which are shown as these triangles. So using these formulas, we could obtain the predictions from our emulator, which is this black curve, and the uncertainty on these predictions, which is modeled as plus or minus 2 standard deviation produced by Gaussian process emulator, which is this dotted blue lines. So it's what other Peter's PhD student calls a sausage plot. So the idea is that your uncertainty shrinks as you get closer to your design points. And you can see that uncertainty is quite is close to 0 around your design points. Okay. And so this is a really simple example, and I think as Danny showed, not only Danny showed last week, you can build emulators for more complex models, but this is just a sort of a general framework. We could use emulators, and we can use them inside for calibration, in particular for history matching. So again, as before, we try to define our computer model as a function that takes inputs as a vector x and outputs f of x. And we proceed to specifying a statistical relationship between some observation z and the computer model f of x. So in this case, we specify that as a sum of your computer model output plus some model error, so your model discrepancy, and plus the observation error. And as before, we model Gaussian, your f of x as Gaussian processes with the mean and covariance function, and model error is just 0 mean with specific variance, and observation error is 0 mean with variance.
The small error is 0 mean. Is that something you can just work? The small error is 0 mean. Is that an assumption, or what was it?
Yeah, it's yes, a statistical assumption.
Because a model as well can be strongly biased and always overestimate, for example. Or
I think if it's biased, it comes inside the variance. Yeah.
No, it's 0 mean because you've got a mean function. So the hx beta term is taking out the deterministic part.
okay.
It's 0 mean around that function.
Okay.
Well, no, it's not necessarily 0 mean. It's 0 mean in the prior. But if you actually knew if you knew your model was 1 degree off everywhere, you'd just change it to 1 and it wouldn't change the framework. But by default, we put it at 0 in the prior. Obviously, it will be whatever it is.
Sure.
And then you can perform, using this framework, you can perform calibration by using history matching. So the idea of history matching that you're trying to rule out regions of input space, parameter space that are too far from your observation z by computing some distance space matrix, which is in this case implausibility function. So the implausibility function has this form where z, as we defined previously, is your observation. Variance is your variance on your observation error, and this is variance on your model error. And expectation variance are produced by your emulator. So in the ideal scenario, if you have perfect simulator that you can run fast everywhere in the input space and explore everywhere in the input space, you didn't need to compute your, didn't need to construct your emulator, and this will be just f of x. And you wouldn't need to have your variance because you could run your simulator everywhere. But in the real world, when we deal with really complex computer models that takes hours or months to run, we have to construct emulator. So in this case, we use a prediction produced by emulator instead of f of x, but we also need to account on the uncertainty on that prediction. And in order to find this, in order to rule out this parameter space, we need to compute this implausibility function across the input space. And in the end, we derive not ruled out space for which implausibility function is less than or equal some threshold a. And the idea is that in this reduced input space, you could have points that are actually, for which actually there is an agreement between your observation and your computer model runs, computer model output. But also you can get points for which we're really uncertain about computer model behavior.
Try lifting the blackboard up, putting it down. Right, so
It's up here on computer itself. Oh yeah.
good call.
Okay, so
Looks like a loose cable.
Yeah, it does look like a loose cable.
so basically the idea that you might end up with some points in this region for which you have really high variance on your emulator prediction. So most effectively, the history matching method is when you do it iteratively. So the idea is that you need to perform it, it's called multi-wave history matching or refocusing. So this whole process of obtaining wave 1, where we have to construct emulator, perform sample points in the input space, evaluate your implausibility function at these points, and only choose the points for which the threshold, for which implausibility function is less than or equal some threshold, and count this space. You can repeat it k times.
And how do you choose the threshold?
So the classic one is to set a at 3, which is some 3 sigma rule, where you think that your unimodal continuous distribution, some points lie within 3 sigma random value. But I saw papers where they vary the threshold as they go further down the waves. Yeah, Danny is noting, so yeah, it's all good. So the idea of refocusing is you cut down your space, let's say at wave 1. You sample more points, you choose more design points in this reduced input space at which you're going to evaluate, you produce more computer model runs at this reduced input space. You reconstruct your emulator, and you are hoping, in the ideal case, that because you cut down the space and you reduce the density of your computer model runs and your design points, your variance will decrease because you're focusing on a reduced space. And when you compute your implausibility function, this reduced space will cut more points out, for which previously the variance was quite high. Your uncertainty about computer model behavior was quite high. And you repeat it k times, and k depends on your budget, how many computer model runs can you produce. So yeah, this is the basic idea, and you gradually reduce your input space till.
And if you would make this k very, very high, you would not end up with 0, an empty space.
I think yes. You mean that it will cut everything else?
Yeah.
Maybe.
Well, it
Depends
could
how
do
well the
if your model doesn't
discrepancies-
fit. But if your model does fit, then these are the
Then
points which
it
survive.
converges to a stable
Yeah.
space.
Yeah, it will converge to whatever the zero uncertainty on the emulator space is. So as soon as you write your discrepancy in your error down, you can imagine that implausibility function where you put in the model and you took the emulator to 0 as that defines some set, some unknown set, and it should converge to that set in the end, of course. Whether you can ever get a 0 variance emulator in high dimensions.
And again, there's a really, really simple demonstration of how you can do iterative refocusing on a 2D toy example. So the idea is that you have this half a sphere function, and here's your observation, which is a red line, and this is your plus or minus two model variance and model error, and variance on your model discrepancy, which in my case I just define 0 because it's a toy model. And the sample size corresponds to the 10 design points for which we can use to construct an emulator. And because it's a really simple toy model, I know the true N-way size, which in this case I define true N-way size as defined for points for which implausibility function, where instead of expectation I use a computer model, so this toy model evaluation, and I don't have any variance on my prediction. So it's the true N-way space is 5%.
What's lambda?
Oh, that's a good question. So basically, because it's two-dimensional example, this is just a cross section. So at wave 1, as we said before, we have this 10 run maximum design, and we constructed our emulator, and we cut it down to 15.56% of original input space. So in this plot, this is input plot x1 against x2, and this brown squares corresponds to the design point that I used to construct emulator for wave 1, and I only cut my input space down to this light gray region, which contains inside this true N-way space, since I know, and it's really simple toy model, but it still has a lot of space that shouldn't be here. So I decided to perform second wave of history matching. So the idea is now I can sample more points that were inside this space and update my emulator. And now I cut down my input space down to 6.10% of original input space, which is close to the true N-way space. So it all seems to be really easy. It's okay, great, we can build an emulator for sine function, we can do refocusing for half a sphere function, so surely there should be some motivation why we need to do it and some connection to actually some work with a complex model, climate models. And in particular, throughout my PhD, I worked with within a HiTune project, and the idea was that HiTune project was with French Climate Center, and they were really interested to improve the cloud representation and the radioactive effect in the global climate models. So the idea that it's really hard to model and include the effect of clouds in the climate model, because clouds' behavior and their effects are their subgrid processes. And usually, because the physics of clouds, it's so hard, they usually are counted by parameterization, some approximation equations that tries to model the behavior of ensemble of clouds inside this grid. And in particular, they were focusing on boundary layer clouds, which are low-level clouds. And they play a really important role in the water and energy cycle of the atmosphere. In particular, something to do with their radiation. So basically, they reflect shortwave radiation back to the space, but they stop long-wave radiation from escaping the Earth, and that controls the cooling of the Earth. But most importantly, tuning of these clouds are crucial for two main reasons. So, firstly, it was shown that they contribute to persistent and systematic biases in sea surface temperature observed in the climate model, but also they largely account for the spread in the climate change predictions. And there's some cool pictures of boundary layer cloud that they produced themselves on one of the computer model in Métier, France. So they wanted, the aim of the HiTune project was to provide climate community with some clear framework how to do process-based tuning of boundary layer clouds. So the idea is that there are two types of tuning: global tuning, where you simulate on a big global climate model, which takes ages, and they were not even sure, because this model is so complex, whether things that they were producing explains their boundary layer cloud behavior or their representation. Instead, they decided to focus locally on the boundary layer clouds by comparing single column model to the large eddy simulations that tries to explain clouds behavior.
Can I just ask, I'm not really clear whether clouds are an input to the model or an output of the model.
They're not inputs and outputs to the model. So basically their behavior is modeled through some equations, through parameterization scheme. And we're interested in this parameterization scheme. So there's some inputs of this parameterization scheme that we're going to emulate, and we're interested, and we treat them as inputs to the function f. And outputs are some characteristics that they try to model, to include in the climate model, that corresponds to this radiative effects of the clouds. So you can't include the cloud's behavior, every single cloud behavior inside your climate model, because it's really complicated. They're like these small subgrid processes. So what they do, they try to model the behavior of an ensemble of clouds using some approximation equations. So it's not even like real. It's some like approximation that they try to learn about.
So your data Z, you're going to be comparing to is not clouds either.
No, they're not clouds, exactly.
Your data Z are like the albedo of the clouds or something, the overall effect of them.
Yeah. So they're not even real clouds. So
I don't think this is true.
What do you think it is, Danny?
Well, I mean, the large eddy simulation is simulating clouds at a really fine scale, and the single column models, they are simulating clouds, but they're like a sort of convective equations, and then they have a number of these going on. So they are clouds in the model. They're just not what we would recognize as clouds.
But what's the actual variable in the end? Is it liquid humidity or not humidity? What is it? Because in the end it translates to a variable and then a number, and you fit to the number. So what's in the end the representation of a cloud? Because a cloud is just liquid little droplets, right? So somehow it's, I suppose, a continuum phase in the LES, on the grid point. But then the question is, what's the variable which you're actually looking at as a proxy or as some realistic thing for clouds?
it's not a realistic thing. It's some summary of the collective behavior, like the velocity or cloud cover. It's not individual cloud.
Those things are computed, so you get temperature and momentum
Humidity,
and
what temperature
humidity
and
at every
momentum.
input box. And so
But I think you said on your slide there, Victoria, that you're interested in the radiative effect of clouds.
But even
Right,
that,
that's basically what you're interested in climate models, is clouds because of their radiative effect. What they do is the shortwave, what they do is
I know, but in the end that must translate from the LAS model to a variable. So what's the variable? I
Well,
don't think they model radiation. The radiation is inferred, say, from the temperature, combination of temperature and humidity. And so that means that temperature and humidity via a formula gives you some variable, and that variable you tune to. So I'm just curious what that variable is.
well, they tune to lots of different variables.
Well, that's okay.
So
yeah.
they take the raw 3D output, and then the whole workshops on which key metrics sort of give you the best idea of the clouds. But in principle, you do get 3D representations of
Because in the end, it's a variable which might be a combination of variable function of variables in your LAS, and that's what you tune with. Otherwise, you have nothing in your hand. I'm a mathematician,
We
so
tune with
so
lots
so
of-
are you, right? In the end, you need numbers in your hand. How do you get the numbers?
Well, you derive them from 3D
I-
momentum, velocity, temperature. So
No,
so
not
they
momentum,
use.
velocity, and temperature.
So-
Those are not involved. It's temperature.
They
Where
actually
then?
are.
It says compute the estimation of radiative effects of clouds from LEAs, which corresponds to the radiative effect matrix. So there are feedback factors from clouds, long wave and short wave feedback, you'd like to get right. And you can't get right with a low resolution model unless
You know, I
you
understand.
calibrate it.
But the word radiative effect is a set of words which underneath it relates to the variables in the LAS. I'm just curious what they are.
So, for example, we use the
Because
boundary
you
layer
use Planck's
potential
law or
temperature
whatever,
at
right? Whatever law
some
you
number
use.
of hectopascals.
Well, so,
And then it's temperature and something else, which I forgot.
well, it's actually, it's the droplet distribution, droplet size distribution, that's what you really need. But you just can't do that in a low resolution model, so you're trying to
Yeah.
short circuit it and emulate the thing you're after
Yeah.
rather than simulate individual, so this, anyway, sorry,
No.
personal conversation.
No, it isn't. Because it's relevant.
So what would be the data? What is observable?
Well, that's
At
what
the
I
day?
exactly.
So
That's
this
Well, there
was
is
what-
an-
LAS simulations.
There's a proxy
There isn't
observation.
any
Okay.
data. They're calibrating the climate model for the LES.
Yeah.
Yeah.
So the climate model's a low resolution model. It can't model the clouds. So you model the clouds in the LES and you treat that as the data,
Okay.
and you
Yeah.
calibrate the climate models of the LES so you get the same cloud effect.
Yeah.
You can't model the clouds.
Yeah.
But the cloud effect is much better because you
Yeah.
calibrate it to the LES.
So the
The
LES,
LES
is
is proxy.
the LES, sorry, I missed
Oh,
that.
large edge simulation.
And that's for a small
It's a
region.
high, very
Yes.
high resolution
For a small
mid-band
region.
model.
And they do them over different types of boundary layers. So over the sea, over the desert, over the forest, because you get different cloud characteristics over the boundary layer. So the idea is you've got lots of different types of boundary layer. You've got these standalone LES simulations, and how do you figure out what the parameterizations of all of these clouds are so that they can simulate all these different things well? And so that's what they're doing.
But they gave you data, what made those numbers, right? Did they tell you what those numbers are? They just call them R radiation or something.
No, they give me numbers, but I have no background in physics and maths.
No,
It's
but
very
what-
limited.
So what did they say? What the numbers were? I mean, what did they signify? Did they tell you anything?
Yeah. It's like cloud cover, but it means
Okay,
not much to me.
alright.
Even if it was not cloud cover, I don't know.
There's some cloud scheme inside the French climate
Yeah.
model. We don't
But as
understand that.
a general point of calibration, with these complex models, we generally try to calibrate against all the output variables that they produce, in order not to bias towards a certain submodel being better at the cost of other submodels becoming worse. But I guess that the strategy here will be not to look at all the output variables, but at some which are a bit more relevant for inferring information about cloud behavior. Or
So there are two things to say. I mean, firstly, we don't do this. They do it. So we've given our tools over and worked with them for a long time so that they choose the metrics, they do the emulation, they do the history matching, and we just explain what our tools are saying and help them integrate them into the model development. when we've tested this with them in initial workshops, they've emulated things like boundary layer potential temperature at a certain number of hectopascals. They've done the boundary layer height. They do integrated quantities. They do when do the clouds get to a certain height in the simulation. Various things that they've decided to do. And at the moment there are about 10 or 20 that they try to match all in one go. So they do what you say, but we're not it's not our, they're not our decisions, and it's difficult for us to answer the physics questions because it's not even, we didn't even do any analysis.
You provide the tools.
Yeah.
It's just black box for them.
So are you able to say what are the common variables that are going to be, what are going to be the inputs to the coarse resolution climate model that are common to both models? So you can, okay, you don't have all the processes in the coarse resolution model, but you must have some of them that you're going to be able to feed the coarse resolution model with.
Temperature and humidity profiles mainly in the atmosphere.
And what kind of land cover it is, because you said that they have different models.
Well,
or what kind of ecosystem it is.
But they were mostly interested in, they have different cases, and these clouds were like over ocean cumulus clouds, or over continental USA. But we give them tools, we explain them how the picture looks, but they are the experts who choose what matrix to consider and what cases to consider together and what not.
yeah, that's true. And the inputs are parameters to the equations driving convection in the global model. So you take the large eddy simulation as that's truth, and then the global model, you take a column out of it and you try to tune the parameters of the equation so that you get something that's compatible with that truth. And then you stick it back into the 3D simulation and you see if it did anything, and so on. But there's no, I don't think they have ecosystems in the global coupled model.
They do, but they don't have the LES actually. But in the
In
LES,
the French model, it's atmosphere
Yeah.
only.
Yeah, but it still have a land surface.
Yeah.
The atmospheric models include a land surface.
But I suspect it's only albedo that's going to matter.
Yeah, I mean,
Yeah, they'll know the colour, they won't know the
Yeah, I mean,
color.
so you imagine that you could simulate the atmospheric profiles, knowing the land cover, even at low resolution. And then you say, given that mean atmospheric state, what would I need to do to make it produce the cloud cover and the cloud effect, the radiance effect, that you get in a high resolution model? That's the basic problem. It's absolutely the biggest problem in climate projections, you probably know. Big deal.
I think the idea is just to present how this statistical tools are powerful and they could be applied, because I'm not an expert in cloud, so I guess people who publish history matching in HIV are not experts in HIV or, I don't know, galaxy models, or maybe they are. But the idea that you could use these tools, but you're an expert who can make decisions for you which metrics to choose or which are what.
Do you know what, I just wasn't.
Switch.
I'm not clear now what the inputs and outputs of the model is, and that data isn't actually data. That's what I wanted to know.
Yeah, it's property data.
So their job was to provide us with some data, and our job was to give them statistical tools to actually perform this robust tuning. So there's a paper by one of the leading climate scientists about tuning and what the tuning framework within the climate community, and there are some climate groups that still do tuning by hand, and they were really wanted to show, well, there is some mathematical framework that you can adopt, and there are tools that we're using to do process-based tuning based on emulation, history matching, and refocusing. And that led to the development of Exeter UQ tools that are actually now available from today.
See what you done last night.
Yeah, from Monday. So it's now publicly available on GitHub, and actually I can send all of you links and you can have access and play with it yourself. But the general idea is yeah, so the general idea that so the framework is pretty simple. So you have this build emulator directory that will help you to build and construct emulator, has all the necessary stand files. So we do it in a fully Bayesian way. We define priors in our Gaussian process hyperparameters, so you don't need to worry about it, and it's all pretty robust and was proven by our collaborators. So you can play with time series vectors, for instance, so you can play with spatial fields. The code is provided by Danny's postdoc James. Then you have a history matching folder, which has all the R files that helps you to produce pictures for history matching and perform history matching. I mean, in terms of computing implausibility. And then there's a demonstration folder where you have available LMDZ data sets where you have simulator outputs, simulator inputs in an R data file. But I think I would focus on in examples where actually there's two markdowns that will go through the idea how you emulate using our tools and how you can perform history matching using our tools. It's pretty easy. You just can clone it and download it as a zip. I did it many times to test it.
Do your examples use quite big data sets? Can we do it on our laptop, or is it a bit big for that?
It does, so the data set that it uses, it has 80 simulations and one output. But I think we can do larger data sets.
I like small ones.
Oh, you like small ones? Okay. Yeah.
For the example, the question is, does the example just run on a laptop?
Oh yeah.
That's the answer.
Yeah.
So you don't use a big server just to run.
No. It's
Chris?
pretty easy.
The client modelers do this on their laptop. And I think they have many more simulations than 80.
Can you say a bit more about how the algorithm for identifying the NROI, the not ruled out yet points, works? I think the reason I ask is this seemed quite similar to my question about doing optimization in high-dimensional spaces when you've got uncertainty over what the objective function looks like. It sounds like quite a nasty global search problem, but I've never really thought about it very carefully.
To find the NROI space.
Yeah.
I mean, here we do it pretty simple. We just generate lots of points across the input space, and at all these points we relate this implausibility function and just restrict it to less than.
But that implausibility function, maybe you can say a bit more about that. So that has these variance terms in there, and these variance terms, are they chosen or calibrated?
So currently you have to choose this manually because especially model discrepancy, it's quite hard topic. How do you find your variance on model discrepancy? But variance on observation, it's also given by the collaborators to us. So you can input it inside the model, but it's not estimated.
So the algorithm does not teach you about the magnitude of the discrepancy. It just, you have to assume a certain variance associated with it.
Yeah, but because the tools are quite fast, you have an opportunity to explore different values of model discrepancy and see how your parameter space shrinks when the model discrepancy changes. But I think there is going to be a paper on model discrepancy.
I hope so. Not my
So do you choose the input, the sampling points for your X randomly, or if you've got like you've got a hypervolume, you'll do less Latin squares or something?
Yeah, so we implement Latin hypercube, so we want to maximum Latin. Yeah, maximum Latin hypercube to choose design points.
To evaluate the implausibility or to
No, to
So
find
each time,
design.
each round when you want to choose
the model
choose
runs.
Yeah, the
design
design.
points.
The design. Yeah, so the design generally, there's lots of designs you can use. We tend to use maximum Latin hypercubes, if you know what that means.
For wave
I know,
one.
Yeah,
I
you
know what
the
Latin
words
cube
are.
is trying to be, yeah.
Yeah, I mean, we can go through that if people want to. We can
You
talk
can
about-
go.
we can talk a bit about design.
So the,
Uh,
well, so my next one was going to be, what do you do, if anything, about variables being highly correlated, or rather their outputs being highly correlated?
we want them to be highly correlated because that's what the Gaussian process is telling you. It's modelling the correlation between those points. So we actually want them to be correlated. We don't want them to tell us the same thing because that's a waste of a run.
I meant the different variables in your hypervolume. They can be correlated.
Yeah, so we
Answers, isn't it?
we don't really use maximum Latin hypercube, so not in our software. We use stuff that checks things like the eigenstructure of the design to make sure that you don't have any of that. And you can never check that some higher order combination of them isn't completely correlated because you don't get enough. You don't have enough runs per for the dimensions that you're designing normally to do a super good job with that. And anyway, that's what we do for the first pass. When we get to the second pass, and we've got this weird shaped space, and you have to do what Chris was saying and find it and get points inside it, and then you would like those to be kind of far away in some sense. So that becomes a whole research problem in itself, and half of Victoria's thesis so far. But I guess she's desperate not to talk about that. So.
I can talk about it. It's an experimental design, so it takes longer to find where to run your points at next iteration of waves than actually run a climate model. So success.
You want a space filling design with as few points as possible.
Yeah.
And when we start the first run, that's a hypercube,
Yes.
and that's relatively easy. But then the second wave, we're now living inside
We
an
only
enroll
shape-
space,
then-
which we actually only have a membership. We can tell whether any points inside or outside, but that's all we can tell.
Yes.
So we now want to put some sort of space filling shape
Yeah.
inside something we don't know the geometry of. And
Yeah.
Victoria has
the
some very
shape-
clever methods
yeah.
to do that.
Sounds cool, yeah. And the shape also tells you something interesting about the structure of the model. The shape
Yes.
tells you which variables are likely to be correlated.
They are very complicated usually.
Yeah, so I can just quickly go through one of the R markdowns, and it's actually showing some output of inputs and outputs of a climate model that we are working with, single column model, but I don't know what the output actually means. Sorry about that, and inputs as well. But for French climate models, it was really meaningful. So also this vignette kind of explains how to use our tools, but I think you can do it in your own time, or you can ask me any question after. So yeah, so in general, we just start with loading our built emulator tools that contains all R and stan files used to construct, emulate, and do diagnostics. And we load the data frame. So you can see. So the first 6 columns corresponds, so it's 6 input parameters of this parameterization scheme. And the last column corresponds to the output that we're trying to model response that we're trying to model. And there is this extra noise parameter that I'll explain a bit later, so it's not an input of a climate model. Then we proceed to actually visualizing what the model response looks like. So we use 80 points to construct our emulator to model this model response. So we plot output against input. This is just a simple scatter plot, and you can see that there's a strong relationship against this input. Nothing really meaningful going on around this four, and again, a bit stronger relationship with this input. But it's just based on the eyeballing. So again, the next step, we have this wrapper to construct our emulator, and because we are working with complex response, the way how we find these regression functions, h of x, that you asked me for, is actually using stepwise regression to derive the form of these regression functions. So they could be squares, it could be a Fourier series, and actually this noise term that you saw before, it's like a stopping criteria. So if when we use this stepwise regression, we pick up this noise term, it means we stop adding more terms. Yeah. Yes?
Yes.
And then we actually do the whole fitting of emulator using this stem file. So we do it in a Bayesian way by specifying priors on the Gaussian process hyperparameters. So there are lots of packages available in R where they try to derive these hyperparameters, Gaussian process hyperparameters, by using maximum likelihood estimation. But there's one particular discreting that's really unstable. So there's an issue with one of the parameters. And we found that if we use stan, we specify non-informative priors that restrict some crazy values for parameters, it's more robust. And our collaborators didn't have any problems with our tools so far. I mean, they had lots of problems with stan, but not with general predictions. And also because we're doing it in a Bayesian way, this is samples, posterior samples to check that. So this is hyperparameters in the Gaussian process simulator, and it's just to check the convergence of chain. And then in general, we do validation. So we do leave one out diagnostics. So each point, we do a prediction for each point, considering that we remove this point from design set. And black point corresponds to the prediction produced by emulate, and error bars correspond to plus or minus standard error on that prediction. And green point corresponds to the true model value. So they're green with it when the true model value is within the prediction error bars, and they will be red when they're outside. But you can see we did pretty okay. And yeah, this is just running this simple code. We managed to produce these predictions. And we also can do history matching on this particular example, because we were provided with, I can also demonstrate how we did history matching and explain some plots. So the general idea is the same. We load this computer model simulations produced by a single column model, and then we load the one values that they're really interested in from large edge simulations, as well as so it's 3.5, and as well as variance on model error. The only and now we can visualize it together with this observation plus or minus variance on model error. Then, as before in the previous vignette, we demonstrated that we could build and validate the emulator, and after we're happy with the validation check, we can actually use it for inference and produce wave one history matching, exactly using the routine that we described before. But our collaborators, or how we call them, experts, have to define what they think the discrepancy is manually. We also need to specify the cutoff, so that I use the usual cutoff fixed at 3, but again, they can play with this parameter as well. Yeah, and this is where you actually specify your discrepancy and cutoff. then you use our tools from history matching directory to actually evaluate implausibility at the points in the input space. And then you end up with this pretty picture. So the idea is that you're plotting the projection of each input against each other, and the top pictures corresponds to the NY density. So at each grid box, it calculates the proportion of not ruled out points. Whereas in a lower triangle, you can see the minimum possibility for points in a grid box. So this is a picture that our collaborators were really interested to see, because you can learn more about your model structure and the relationship of input parameters for this specific case and this observation. And you can see that there is an interesting relationship between this parameter and that parameter. And I should mention that gray points as well as red points correspond to the input parameter regions that were ruled out completely. So we know that there is no agreement between the observation and the computer model within the error structure. And just after performing wave 1 of history matching, we managed to cut down to 12.8% of the original input space. So imagine that they will be trying to do global tuning and trying to evaluate computer model at this input space, which is like already 80%, would take a long time to figure out that there's no consistency between observation and computer model in what they're trying to show. Whereas now they have a robust framework that confirms it, and it's really fast, that they shouldn't consider any runs inside that regions, if it makes sense. And you can go even further with performing your history matching. So because this single column model is quite cheap, we could produce more runs. So the idea is that we can build emulator for wave 2 by sampling more points inside that region, as I explained in the presentation. So now we again can produce the same scatter plot, and you can see that we reduced our input space significantly, and then we're in a zoomed region. So again, this scatter plot shows exactly the same that we saw before. As before, we have to construct emulator. The only thing that here we see some unusual behavior, so maybe we need to use a different type of emulator. Maybe Dan talked about station emulators, but okay. I have some code, I could show you how to do it. And then, but still, so now you can see there's some red points out there. I will perform V1 now diagnostic. And then we continue with second wave of history matching, and we actually didn't cut that much space. But the thing is that probably we didn't cut as much space as we wanted because of this huge error bars. It could be caused by some unusual computer model behavior. So at the next wave, we could try to use different type of emulator. But
It still looks like 50%.
yeah, seeing okay. But I mean, after tea and coffee, there's code available, and you don't need to run this code. Actually, there's a friendly version, a friendly wrapper that you just can open your terminal, do R script, and it will automatically produce. We can do it together.
How do you do R script? Can you show it? Most of those are.
I meant you don't need to use R, you can use from a terminal. So it's in Exeter. We just do our script. And it's just going to load lots of things. So we
Can you show the script that you just called and what you have to change? So you showed me what you've done, and I thought it was pretty cool. And I guess if everybody had to type all those lines of R and to do it themselves, it would be quite complicated.
Yeah, you don't need to type any of this. So in demonstration, there's user experiment friendly file that calls automatically when you do R script demonstration. So you only have to define your experiment name, your observation name, which corresponds to our data files where you're going to store your simulation, the number of wafers that you're interested in, the cutoff, which is your A, so the implausibility measure, but since we are dealing with single metric, it's a bit irrelevant for us. But when you have more metrics, this becomes more relevant. It determines if it's like maximum plausibility, I'm interested in, or second maximum plausibility. So we can talk about it later when we have actually data with multiple metrics. Sample size corresponds to the number of points in the input region at which you're going to evaluate your plausibility. Here, discrepancy, so this is, again, you define your own discrepancy, and by performing history matching, you can play with more, with different values of discrepancy and see how your plot will change, and try to learn about model discrepancy behavior. And then the name of the metric.
So is this matching a vector of outputs or a single output?
A single output,
Fine.
but it can match
Yeah.
vector of outputs.
And then is your implausibility function then the combined vector implausibility, or is it the individual ones looking at the maps, for example?
Yeah, it's individual implausibilities, so there's no correlation.
There's no fine, okay, that's fine.
Although in there is the vector version for the
Yeah.
spatial stuff, but I don't think Victoria's written a wrapper for that.
Yeah.
If you went into GitHub and showed how you edit that, because I think you've set it up so that people can just put their own data in by editing a text file.
Yes, yeah. So, my laptop. Yeah. So this is there's a friendly wrapper, but behind it there's a more complex, code, but you don't need to worry about it. It will, so just by calling this R script, it will automatically produce all the plots and tell you how much space you cut. Just as a user, you just need to specify specific parameters.
So that's the big R file, but where's the wrapper that people can go and edit?
I just show it. This is a wrapper.
Sure, but for those of us that don't know how to use VIM and how to save it properly and then how to call it.
Okay, it's this one. It's exactly the same.
Yeah, okay. And so if you had your own model runs, you can just edit
Yeah, you
the
just
top thing.
yeah. So you just edit the name where you store your runs. So, for instance, LMDZ8 wave. Why I choose it because if you go, it corresponds to the first LMDZ8 wave, our data where I store the simulation runs. And when I change my wave number in this wave and parameter, it will automatically consider wave 2. And observation name just corresponds to this R data where I store my observation name.
So we just have to explain how to set your data up in that way, and then you can
Yeah, exactly.
press
Yeah.
go.
But